Okay, hello everyone and welcome to the presentation of paper number 233, Optimal Reactive Power Control of Smart Inverters for the case of Vestfold and Telemark Regional Network in Norway. And the authors of these papers are Marta Acosta from the University of Southeastern Norway, Manuel Andrade from the University Autónoma de Nuevo León, Mexico, José Luis Reda from Delft University of Technology, Netherlands, and myself, Francisco Gonzalez-Longatt. Well, today I have the pleasure to be here with you for this presentation, and the agenda is extremely simple. We will start with some introduction where the motivation and the objective of this paper is presented. Then we will go through some reactive controls in the concept of smart inverters, a very brief and very short review about the different control strategies. Then we will discuss about the proposed method here. We will talk about optimal reactive power control. And from there, we will go for some simulations where some performance indicators are used to assess every one of those different controllers that we can find, but also, and more important, the proposed methodology. Okay, but without further delays, let's go for the for business. Okay. As you must be aware, electrical power systems they are right now in a very important and a very exciting time. Because as you must be aware, electrical power systems are changing, and the changes are basically the full transition from the classical paradigm, the traditional power system with huge centralized power generation plants, like hydropower, thermal power plants, and of course nuclear power plants. Okay. Also, from the distribution system point of view, traditional power system has been characterized by unidirectional power flow, and of course, several other consequences like lack of observability and so on. However, in recent times, the environmental pressures are creating the interest to move for a more environmentally friendly generation systems. And that is the reason that electrical power systems are changing, and the integration of renewable is a key point in the transition right now. And all those technology, or the most important part of those technologies, they are using what we call a power electronic interface, a power converter. And those power converters, they are extremely different to the classical synchronous generator. However, they offer a multitude of advantages, okay? And in this paper, what we want to do is, okay, we want to use the new features that we can enable in those power electronic converters in order to provide reactive power control, and as consequent voltage control and voltage control inside the electrical power system. Okay, in this paper we are proposing the optimal reactive power controller that is able to minimize the active power losses inside the network, but at the same time it's fulfilling some requirements, technical requirements, as the voltages in all the buses must maintain inside the limits, but also keeping the control of each one of those converters in order that they stay inside limits. And when we are talking about this is because we believe that the smart inverters, they are able to offer so many advantages, especially after the new version of the IEEE 1547 standard, okay? And what are the different type of reactive power controllers that we can enable in the power electronic converters, okay? Well, if we go to the IEEE 1547, we can identify that there are at least 4 different control strategies. Constant reactive power, very well known, active reactive power, and that is basically a function of the reactive power in terms of the active power, voltage reactive power control, and constant power factor. However, in this paper, we are very ambitious and we want to compare our proposed technology, optimized reactive power control, and we have included 4 more different control modes. That means the ideal constant voltage, the voltage Q drop, the voltage IQ drop, and finally one that is extremely interesting, that is phi P. Phi is the angle for the power factor that we use, and P the active power. Okay. Here in this slide, you can see the description of each one of those reactive power control strategies. However, you can read the full details inside the full paper. And here we have again the full description, okay? All the equations, they are implemented, all the equations are considered. However, the important part here is our proposed method, and we are trying to use an optimization problem to solve the reactive power control. In this case, we create an objective function. The objective function is located over here. Is basically minimizing the active power losses inside the network by adjusting the reactive power production or consumption of every single of the smart inverters inside the network. However, here, as you can see, the reactive power considers the limits that you can find in the inverters. And we have formulated what we call the constraints, and those constraints represent the voltages in every single node inside the network. The idea is that we are minimizing the active power losses by controlling the injection of the reactive power at the time that the converters are inside safe operation, and we ensure by a combined constraint that all the voltages inside the systems, they are inside the limits, okay? Well, and now what we will do is define 2 different indicators. In this paper, we are considering 2 different indicators, one related with the voltage profile. We are using a very well-known concept, and that is voltage profile index. And also for the energy losses, we are using a very simplified but very useful equation to calculate the total energy losses inside the system, okay? Now it's time to present some results. And for the simulation case, we are using the regional distribution network of southeastern Norway. You can see here the representation is basically a lot of loads at the southern part, and we have a lot of hydropower plants around, okay? Our network was implemented and 58 solar power plants were included inside the test system, okay? The idea was to challenge the optimization method, challenge the mathematical optimization in order to get the solution for a very realistic network. Then we define several scenarios, simulation scenario, considering different type of controllers, okay? And I will focus mainly in this presentation in the number 9, okay? Number 9 represents the optimal reactive power dispatch, the optimal power control, the reactive power control that we propose in this paper. As you can see over here, as you can see in this slide, you can see right now the voltage profile. In this case, we are using the voltage profile index during 24 hours. And as you can see, there are 2 very important conclusions here, okay? As you can see, there are some controllers that they have very bad behavior because they try to move away from the ideal situation near to 0, okay? That is a really bad response. However, if you look the case number 9 in black color, that is the proposed optimization method. And what is the surprise? That is behaving extremely well and is keeping constant the voltage inside the limits, okay? Then we run another simulation. The next simulation is related with the active power losses. And as you can see over here, the proposed method is allowing a massive reduction of 16.91% of the active power reduction, okay? Finally, here there is a summary, and in terms of energy losses, the proposed optimal reactive power control is the best control that we can implement over here, allowing a reduction of 13.7% and of the total energy loss referred to the base case. This paper has been successful on presenting and proposing an optimal control, reactive power control. And this reactive power control has been implemented and has been tested using numerical simulations, and numerical results indicate the suitability of the proposed approach in order to minimize or reduce the energy losses at the time that is fulfilling the voltage constraints, okay? Thank you very much, everyone, for watching this video about this amazing paper about optimal reactive power control of smart inverters, the case of Vestfold and Telemark regional network in Norway. Thank you very much.